Okay, so after getting some background on electromagnetic radiation, we can go back to studying the modes of the atom. Before we get to the latest one, we still need to see Bohr's model of the atom, okay? But that requires understanding a little bit about electromagnetic radiation, quantation. Scientists, not just in the late 19th century, but they have been struggling understanding light and especially understanding the light emitted from atoms and molecules. When you heat up a molecule, they usually emit the excess energy in the form of light. Okay? So you'd expect that you have a range of energies, you produce a continuous spectrum. Like if you're looking at white light, that's the spectrum that you get. There's an instrument that you can put a sample in the gaseous state, run electricity through it to give energy, and then the particular sample emits light, and you can actually see it on a screen and all of that. If you have it full of white air and then nothing but light in there, that's what you get, a continuous spectrum. The problem is when you put a particular element in there, then you don't get a continuous spectrum. Okay? You get discrete or line spectra. You get only lines instead of all of the colors. Lines that appear at certain wavelengths and they have different colors. And what is very important, each element has its own set of lines. Those lines are like an ID. You have sodium, and you can see the lines when you put sodium. Hydrogen, these are the lines for hydrogen, calcium. Actually, we used to do that in the lab. It was real good. We gave the students like 10 different elements, and they wrote down the color of the lines, the wavelengths, and then I had a number of unknowns, and by looking at the lines and comparing to what they have seen before, they were able to identify an unknown. Because this is like fingerprints, okay? These are lines, but they can be used as a fingerprint. The problem was, how do you explain individual lines instead of a continuous spectrum? Okay? Basically, every line is a single wavelength, because we said the wavelength or the frequency determines the color in there. So the gas is emitting energy in sets of discrete energies. It's quantized again. You don't have every possible energy. You just get, in some of them, 2 or 3 lines, 2 or 3 energies that are emitted, and that's it. And that was very confusing because classical electromagnetic theory says that you should only get continuous spectra, but that's not what scientists were observing. So maybe the classical theory doesn't work when we're talking about light and atoms. Rydberg was the first one who came up with a formula and found that if your instructor and non-instructors who expect the students to memorize it, I usually give that. But basically, he said, when you have these two numbers, those are integers, and I'll be back to them. This is Rydberg's constant that he calculated. You can calculate for a particular transition what wavelength you're going to get. These were numbers that he actually calculated for different elements. Okay, so he said you have different levels of energy, and you call them N1, N2, N3, or something like that. But these numbers were different from every element. So he had a giant table where he had all of the possibilities, and saying when one electron moves from one level to another level, something like that, it emits light. And knowing the value of this number and knowing Rydberg, he could calculate the wavelength and the color. And he was able to predict hydrogen's emission lines perfectly. Now, the problem is he did look at emissions in other elements and it didn't work. Okay? But it worked for hydrogen. And once again, you get the idea that since these numbers are integers, you have only specific frequencies and specific colors and specific energies too. So that explains very well that. He didn't know what those numbers were. Like I said, he just figured out if these are the number that I come up with for the wavelength matches perfectly the spectrum from hydrogen. So that equation does have some value, but he didn't know what those numbers were. Bohr was able to explain it in there, and he's the first one to say, we need to forget about classic physics, classic electromagnetic radiation. That was the beginning, the birth of quantum mechanics. What did Bohr say? Well, before, let's review what we know about. We said that the atom has a very small nuclei, very dense. It's surrounded by the light and very small electrons that are moving. But this description is incomplete because an electron orbiting around the nucleus would be accelerating. And you say, wait a moment, it doesn't change the speed, does it? No. Keep in mind, this is physics. Acceleration means change in velocity, and velocity is directional. So when the electron is moving around down, first it's moving in this direction, then it's moving in this direction, then it's moving in this direction, even though the absolute number may be the same, because it changes direction, it's changing velocity. So it's accelerating. Okay? Again, this is physics. You just have to take my word for it, okay? But if an atom is accelerating, it should, or the electron is accelerating, should be emitting electromagnetic radiation. Again, this is regular physics. And if it's emitting radiation, it's losing energy, so it should start coming down at a smaller orbit. So basically, the electron will be orbiting, and as it loses energy, it will start making smaller and smaller until finally collapses into the nucleus. But we know it doesn't happen. So Niels Bohr tried to figure out, obviously classical mechanics is not explaining what we are observing in here. So he got Planck's idea of quantization, and he said, oh, what we're having is energy levels. And remember, Einstein was talking about you have photons that the energy is proportional to the frequency. Yeah, the electron is on an energy level, and it doesn't emit any energy. I can't explain why it doesn't emit, he said. The only thing I can tell you, this is not classic mechanics, okay? But you have different levels, he called them orbits, and when the electron is in an orbit, for some reason that he didn't explain, it does not emit or absorb any energy. Now, if an electron moves to another orbit, it needs energy to move to another orbit, so it absorbs energy. When the electron returns to that orbit, it releases the energy. But you don't have any orbit that you want to. You have this orbit and this orbit and this orbit and nothing in between. They're quantized. There's certain energies that you can have an orbit, but you cannot have anything in between. Okay? The energy, whenever the difference energy between two different orbits is going to be different between two of them. So once again, if an electron is returning from a high orbit to a lower orbit, it releases energy, and we say energy is related to the wavelength or the frequency, so that gives you different lines. You have only a number of orbits that you can jump from or jump to, so you have only very discrete energies, and you only get certain wavelengths. Okay? And he did that for hydrogen, and it worked real good. The energy is going to be the number of the orbit times this constant. Don't worry too much about it. He combined in there the electron mass, Planck's constant, blah, blah. But he said that the energy is going to be proportional to the orbit number. So one of the things that he emphasized in here is that matter is more stable at the lowest possible energy. So an electron in the lowest energy orbit, n equals 1, is very stable, and we call that the ground state. Now you give it energy, it can jump to a higher energy level, to higher energy orbit, and we call that an excited state, but the excited state is unstable, so the electron eventually is going to return to the ground state and releases that extra energy. That extra energy is going to be released as an electromagnetic radiation, and depending on the amount of energy, you're going to get different wavelengths. Okay, so we say an atom absorbs energy as a phone. The phone has a certain amount of energy, a discrete amount of energy, jumps from one energy level to a higher one. When it returns to low energy, it releases that energy, and again, it's a discrete amount of energy, so you get a particular line spectra. And he was able to determine how an atom works, and everything worked out perfect. Okay, let me show you here. I know this is a diagram. Remember, you have only one electron, so usually the electron is going to be in n equals 1. But if you give it energy, because you're giving quantized amounts of energy in the photon, it can jump to n equals 2 or n equals 3 or n equals 4. Now, when they return from 2 to 1, there's only one transition, but if it's in 3, it can return directly, or it can go from 3 to 2 and then from 2 to 1. So you see that there's different transitions. Every transition has a different energy, so that causes a line. And like I said, this works perfectly to describe hydrogen. You can explain all of the lines in the hydrogen. You see this, but you've seen a bunch of transitions in here, and let me go back when we was looking at hydrogen. Hydrogen has 1, 2, 3, 4 lines. Well, these are visible light, okay? Many of these energies give lines that are beyond the visible, so this instrument cannot measure them. So there was no problem. Everything worked out real good. If you want to do some calculations, what is the energy and the wavelength of the line when you move an electron from the orbit n equals 4 to n equals 6, how much energy has been absorbed, and in what part of the electromagnetic spectrum you find this radiation. Okay, so they give you the value of K. We said the difference in energy is this. They give you the value for N1 and N2 in there. So just plug in the numbers, do the calculations, and that tells you the energy. It's positive. Why? Because the electron is absorbing the energy to get excited, because it's moving from one level to a higher energy level. Now, once you have the energy, you can calculate the wavelength, right? Using Planck's constant. So he calculated the wavelength, and then looking it up, it tells you that it's in the infrared portion. You will not be able to see this line with the regular spectrometer. It's infrared, but you can calculate the line. So Bohr's model worked real good. He predicted and matched all the visible lines. He predicted invisible. It's perfect. The problem was when he moved to the next atom, helium, that has 2 electrons. It didn't work. His predictions didn't match the experimental evidence. Oh well. Then he realized that there's electron-electron interactions. Once you have more than one electron, that's going to affect things. The problem with Bohr's model is that he was talking about precise orbits. An orbit is like a path that the electron is going to follow, and it cannot deviate one little bit from that. The moment you have electron-electron interactions, you cannot extend your orbit, so Bohr's model only explains the hydrogen atom. And you say, well, considering how many atoms we have, it only explains one. What good did it do? Actually, it was very good, because for the first time we talk about the energies of electrons being quantized. So we are going to describe the electrons by what we call quantum numbers. The quantum numbers are integers that describe the arrangement of electrons in an atom. And they're very specific numbers. Electrons can be only located in a certain position, a certain place, and they cannot be in between different energy levels. He also said that the energy increases with increasing distance from the nucleus, and he explained, like I said, the spectra, the lines of the spectra, has been the result from quantized electronic energies. So he basically changed the way people were thinking about it. Even though his model was limited only to hydrogen, he got a Nobel Prize. And people understood that when you're dealing with a microscopic world, you're going to have to forget about what you knew in physics and all that and start looking with a complete fresh point of view. It's not going to work the same way. Okay? And that was, like I said, the beginning of the quantum mechanics model that goes beyond classical mechanics. It really breaks apart from classical mechanics. To give you an example, what's the difference between classical mechanics versus quantum mechanics? If you're throwing a baseball, you have a boy here, and he's throwing a baseball. You can't predict where the baseball is going to go, so the catcher will be here when to catch. He can see, he can predict where the baseball is going, and he can go to the right place and catch it, right? Have you ever admired a football receiver? When they run that point, they know exactly where the football is going to be. That's classical mechanics. But you cannot do that with an electron. With an electron, we're going to see that later, you cannot predict where the electron is going to be. You can get an idea where he's likely to be, but not sure. That's the difference between quantum mechanics and classical mechanics. Okay? So, once again, any questions? Make an appointment in Wysan. The link is in the video description. And I'll do my best to explain. I realize this is confusing, but I think we can do it.